morning. Welcome to the 2009 Shannon Lecture. It is my great pleasure and honor to introduce Jorma Rissanen as our 30th Shannon Lecturer, or 31st if you count Shannon himself. When I emailed Jorma to ask if there was anything in particular that he wanted me to include in this introduction, he didn't respond, which I believe was either because he was really too humble to weigh in on what I should say, or he had no idea who I was and so promptly deleted my email unread. Thus, I was left to my own devices in investigating Jorma's past for this introduction. So if there are any inaccuracies, Jorma, you can only blame yourself for not responding to my email. Researching Jorma's background and accomplishments has been a very enjoyable journey, since he is truly a remarkable scholar and what I would call a Renaissance scientist in the breadth of his technical inventions and accomplishments, which span the fields of information theory, systems theory, probability and statistics, mathematics, and control. Jorma Johannes Rissanen was born in Pielisjärvi, Finland in 1932, which is about 300 miles north of Helsinki, so in other words, a pretty cold place. And he completed his licentiate and doctorate degrees in control theory and mathematics at the Technical University of Helsinki, Finland in 1960 and 1965, respectively. So very early on, he was already forging links between mathematics and engineering, which would remain a hallmark of his long career. Jorma's thesis was on control of systems under parameter uncertainty, a precursor to robust control, and he published his first IEEE paper on this topic in 1966. In between his licentiate and doctorate degrees, he joined IBM's Nordic laboratory, which had been recently established in Stockholm, and that was actually the catalyst for him to move shortly thereafter in 1966 from the Nordic labs to IBM's San Jose Research Laboratory in California. This, 1966, was 1 year after Moore published his infamous paper about the density of transistors on circuits doubling every year. And at that time, Silicon Valley was still a relatively sleepy place with far more peach tree orchards than high-tech companies. This would change quickly, and throughout Jorma's career at IBM, Silicon Valley grew from employing about 20,000 engineers, mainly working on microwave tubes and semiconductors, to employing hundreds of thousands of engineers spanning all areas of high tech. Rissanen's early work at IBM San Jose focused on estimation, prediction, and modeling associated with stochastic processes. And in fact, he had an early control paper in 1971 with Tom Kailath on the stochastic realization problem, which is quite intriguing, and you can find it in IEEE Explore. Jorma left IBM for 1 year, which I just found out a few moments ago. According to him, he left because he had an attack of lunacy to go spend one academic year, 1973 to 1974, in a chaired position in control theory at, I'm going to mispronounce this, Linköping University in Sweden. Now, again, according to him, he didn't like Sweden, didn't like being a professor, and he didn't like his field of control. So he left after 1 year and returned to IBM. I suspect, myself, as a California native, that after 7 years of the Bay Area sunshine, he also left because he was suffering from the Hotel California syndrome that prevents you from ever really leaving after you have arrived. Shortly after returning to California and IBM in 1975, Jorma switched fields and invented arithmetic coding, a form of near-optimal lossless compression based on variable length entropy encoding, of which Huffman encoding is a special case that's simpler to implement but less efficient. Arithmetic coding had a deep and immediate impact, which was recognized in 1980 by an IBM Outstanding Innovation Award and by our own society in 1998 with the Golden Jubilee Award for Technological Innovation. Jorma's next and perhaps most important invention was that of the fundamental minimum description length principle for model selection and statistical inference, and this happened in 1978. This MDL principle is a formalization of Occam's razor in which the best underlying model associated with a given set of observed data is the one that leads to the largest compression of the data. MDL is particularly well suited for model selection, prediction, and estimation in situations where the models under consideration are highly complex and overfitting the data is a serious concern. MDL has had broad and significant impact on a wide range of fields, including inductive inference, statistical modeling, pattern recognition, and machine learning. It has been widely applied to a broad cross-section of problems in engineering, as well as biology and medicine, and continues to be a very active area of research with wide applicability 20 years after its invention. Jorma's other two best-known results are in data compression and coding, his 1983 invention of the algorithm context for compression of data with Markov chain properties, and his proof in 1986 that the minimum code word length for any code in a given class is not the entropy, but the sum of the entropy and the code length needed to encode the best model for any model in the class. Jorma has been a very prolific author, not just on these topics, but on a very wide range of topics throughout his career. He has 150 or so published papers and several books, including, remarkably, a co-author paper which is going to appear later this year in the IEEE Transactions on Signal Processing on the topic of MDL denoising. I personally find it truly inspiring that someone late into his 7th decade of life, with so many remarkable accomplishments behind him, continues to dream up new ideas, investigate them, and publish their results. Jorma is not just a researcher, but an inventor, and is named on 15 patents filed by IBM based on his ideas. After retiring from IBM, Jorma became a fellow of the Helsinki Institute for Information Technology, University of Helsinki. He's also a professor emeritus at the Tampere University of Technology, and since 1998 has been a visiting professor in computer science at the University of London. Jorma's many honors, in addition to the ones I've already mentioned, include foreign membership of the Finnish Academy of Sciences and Letters, an honorary doctorate degree from the Tampere University of Technology, a second IBM Outstanding Innovation Award in Statistical Inference, Information Theory, and the Theory of Complexity, as well as the IBM Corporate Award in 1991 for the MDL Principle and Stochastic Complexity. He has paper awards from our society, as well as the International Federation on Automatic Control. He's won the Kolmogorov Medal of the Computer Learning Research Center at the University of London, and of course the IEEE Richard W. Hamming Medal for fundamental contributions to information theory, statistical inference, control theory, and the theory of complexity. So in closing, I would like to mention that Jorma's Shannon lecture is only the second one to be delivered in mainland Asia. The first one was given by Shannon himself in 1973 at Ashkelon, Israel, which of course started our tradition of Shannon lectures. So the pressure is on Jorma as a follow-up to Shannon. I can think of no one more deserving of the Shannon Award and to follow in the footsteps of Shannon with an inspiring lecture. Please join me in welcoming Jorma Rissanen for the 2009 Shannon lecture.
Thank you very much, Andrea. Those were beautiful, beautiful words. I would like to thank the IT Society for honoring me with this Shannon Award. Ever since I was exposed to Shannon's formalization of information in random variables and his other astonishing performance bounds for communication, I wanted to apply them to other fields, in particular to estimation and statistics in general. After all, the central problem in statistics is to extract information from data. Having worked on data compression and introduced arithmetic coding, it became evident that data compression and estimation have essentially a common objective. In data compression, you can't get the shortest code length unless you take advantage of the regular features and restrictions in the data. And of course, in estimation, it is precisely these restrictions and regular features that you want to learn. And it was then quite evident that I could combine them, and I introduced this MDL, minimum description length principle. And I thought that the battle was over. However, when I started preparing this talk, I found trouble. I could not connect the several in themselves meaningful results that people had worked out over the years. I couldn't connect them and to form anything like a theory of estimation. It was like a jigsaw puzzle where the pieces almost fit but not quite. And moreover, some of the vital pieces were missing. Well, after a lot of struggle, I was able to put the pieces together, but I had to change them all. And indeed, the result was a separation of estimation from data compression. So let me begin with a few general, let's see now, a few general slides to set the stage, and they also introduce terminology and notations. So the modeling problem begins with data. They generally come in two forms. Either we just have a set of data points, these YTs, or we observe them together with other variables. They are called explanatory variables. And the objective is to learn statistical properties in this data set Y. And to describe these properties, we describe them in terms of distributions. And every distribution is a model. Now the parametric distributions models cover just about everything. The parameters themselves come in two forms. We have this as structure parameter. A structure is nothing but a subset of these models. And typically, we use these structures to pick the most important explanatory variables when we have them. And then we have these real valued parameters whose number depends on the structure. Now the traditional name for this set of models is likelihood function. I never liked that term. For one thing, I never understood that why introduce something that you don't need. And moreover, there is no such concept in probability theory. I never understood why they use it. The most important problem in this whole thing is, of course, to select the class of models. Now it so happens that the optimal selection is non-computable, so there is not much we can say about that. And here are a couple of typical and familiar examples, I'm sure, to you. The purpose here is to illustrate how you get lots and lots of parameters. So the first is the linear regression. Now we sort, or we have ordered set of these Y values, so we can call it a signal. We span the space of signals by basis vectors and then write the signal in the familiar two-part form. This Y hat is like a smooth version of this signal. It's a linear combination of the basis vectors, and then the rest is noise. And we model the noise by, let's say, Gaussian, and extend by product to the signals themselves. Now, in a very much similar manner, we have this other example, which you are familiar with, these Markovian types of models. Now, we get to this notations that I'm going to use, so we better be familiar with them. Now, to simplify matters, I just denote the data, no matter how they appear, by boldface X. And we also consider only structures that are determined by the number of the parameters, real valued parameters. We then have two types of classes of parametric models, one where the number of parameters is fixed, and the other one where it's not. And to each corresponds a set of functions. There are no restrictions on these, just functions from data into the parameter values. So those are the main constructs. Now we need to address some issues that are significant. There is a complication in such models that parameters determine a model, but not conversely, because it's only the non-zero parameters that actually matter. And the result of this is that the likelihood, I'm using this old-fashioned term simply because everybody uses it. So the likelihood is maximized with the largest possible number of parameters. Well, that's a terrible problem. And indeed, it's a huge difficulty in traditional estimation. Oops. And the next point is this assumption of true distribution or true model or whatever. Customary estimation is based on such an assumption. They think that one of these models actually generated the data. Well, that assumption is not only irrelevant, but it is harmful. It has prevented, in my opinion, it has prevented the theory of statistics and estimation to develop. You will see soon. I'll sketch that very quickly. So we definitely don't want to make that assumption. Well, it immediately has the implication that we cannot measure performance of estimated parameter by some distance to the true, because it doesn't exist. So we need another yardstick, and it will be probability. Okay, this is the traditional theory of estimation on this one slide. There is no more to say. So, seemingly appealing idea, of course, to measure goodness of estimator is the covariance. Because of this famous Cramer-Rao inequality that sets a lower bound for the covariance. Now, the trouble is that the lower bound is reachable only for a tiny fraction of the full class of models. Now, asymptotically, it is reachable by maximum likelihood estimator. And believe it or not, that is the only formal justification for the maximum likelihood estimator. At least I haven't found any other. So all its justification is intuition. It looks good. It's a good estimator. But there is nothing other than that asymptotic verification. Well, now you see that the conclusion is evident. First, let's say the positive part. This surely is a first attempt to create something like theory of optimum estimation. But the covariance is far too weak. It's just one property of the models. And there is absolutely no extension of this type of idea to estimate the number of parameters. So let us show how, let me show how this is typically done. There are lots and lots of criteria, all kinds of criteria. Those are the familiar ones, those formulas, and they are asymptotic to start with. And of course the trouble is that, well, which should I pick and why? No answer given. So now you see that this is the traditional theory of estimation. Okay, so realizing this, the first or a next attempt to create something like a theory was based on coding ideas. And in the idealized setting, in the algorithmic theory of information, Ray Solomonov did the groundwork, even though it's called Kolmogorov complexity. Well, Kolmogorov complexity is simply defined as the length of the shortest program that generates our data. And the programs will have to be self-delimiting so that they form a prefix condition, and that allows us to construct a universal model by help of this Kolmogorov complexity. And the trouble, of course, is, as far as applications are concerned, that again the complexity is non-computable. What that means is that you can approximate it, even by a sequence or approximation, so that the limit would be Kolmogorov complexity. But you can never tell how close you are. So that is a problem. Now, the important property that I'm going to take advantage of is this, that this universal model or code, a code is a distribution, a model, that the code words really are shortest for all data. Now that's quite remarkable when you think of it. Okay, and then there is this general, what I now call general MDL principle, that you want to find a model with which the data, given data set, and the model itself can be encoded with shortest code length. Now that is like a two-part coding. And the first term is, of course, obvious by Shannon's work. But the second term, how to encode the parameters, is another matter. I left it at the time vague and thought that anything decodable is okay. Well, we know that for decoding we need this prefix requirement, which is like generalized Kraft inequality. And of course this principle is very, very general because almost anything can be encoded. But the two problems remain. First, of course, the selection of the way you calculate the code length for the parameters. And the less obvious restriction is that Even if this Kraft inequality holds with equality, the resulting code is incomplete, which is the same thing as saying that it's not optimal. Let me see now. So I have about half an hour left. So this shows how you can apply it to the estimation of the number of parameters. That was the big thing at the time. So we need to quantize the real valued parameters to some precision, and then you optimize with Taylor expansion the precision. You ignore the values of the real valued parameters, you just include the precision. And you get an asymptotic criterion, which is the same as the famous big Bayesian information criterion, where I don't know where the word information comes. It certainly is not Shannon information. Okay, and now we get to the new theory. It may be useful to think of it, the whole estimation process, as analogous to measuring some property like weight of a physical object. The role of the object is played by data. And the property, the weight, its role is played by the estimated parameter values. Now for that, we need a yardstick, which plays the role of the instrument with which you measure the scale with which you measure the weight. And for that, we need a special estimator and the distribution defined by it. I'm going to explain soon how this is done. This is just an overall outline of how to proceed. Well, the large value for the measured properties, these parameters, that's a good fit. And perhaps its analogy would be in this weighing process, would be that I have found the weight of an object with good accuracy. And equivalently, of course, code length can be used as a weight. But the big task remaining is that how do we select the special estimator and get the yardstick? And here is how. First, in the case where the number of parameters is fixed, so we have this special model class, we just calculate the numerator with your estimator and then normalize it, and you got the yardstick. Now this, where you also estimate the number of parameters, it is a little more intricate, and I don't want to spend time on that. Just take my word that this is the way to do it, and you can see that it is perfectly analogous to the previous case. So let's skip that. Okay, now, what are the aspects that we should or could follow in order to pick a special estimate? Notice that we have an enormous number of estimators. Any function from data to the parameter values is an estimator. And we have to pick one function. Well, first, remember that we use this as a yardstick. It certainly must not favor any data, just like a scale must not favor an object. It's got to work for all objects. And hence, the selection must be made from the model class, not from any particular data set. Nevertheless, a good fit means that it should assign short code words to all data. Well, now we got the fundamental difficulty. There cannot be a distribution that assigns the shortest code words for all the data. However, you remember the property of the Kolmogorov complexity defined code. It assigns shortest code words. Given the code, it assigns shortest code words for all the data. So it's a remarkable property. Almost in contradiction to that statement that no distribution can have. Well, those are facts. So, what is going to happen is that the optimal selection of the special estimator will be done by estimation capacity, which is a new concept. Nevertheless, the optimality will be formally justified by theorems, and they are very strong. So, how do we define these estimation capacities? Very simply. Just maximize the normalizing coefficient. And that's it. See, in case you estimate also the number of parameters and you maximize the normalizing coefficient of the thing that we did not elaborate too much, that's enough. Because it also determines the maximum likelihood estimator for the case that K is fixed. Now this is obviously suggested and related to Shannon's channel capacity, but it is different. Okay, let me show quickly an example. Suppose we just have two models in our class of models. Then what we need to do is to maximize, take this breakpoint such that the area under those curves is maximized. And you see that the result is the C hat is the estimation capacity. It's that logarithm of the maximized area. And you construct the complete code. And we have redefined maximum likelihood estimator in terms of these equivalence classes. And this turns out to be very important. Okay, now we go back to the full class where the number of parameters is fixed. So it's clear that this estimation capacity is determined, and it determines, in turn, the maximum likelihood estimator. And it also defines this normalized maximum likelihood code, which originally was defined by Starkov. Now, why would that be good? Starkov used this Minmax argument that he looks for the closest code, this Q, which is, code which is closest to the ideal target, the maximized likelihood, the numerator, which itself is not the code. Now, I must say that his intuition was perfect. However, this Minmax formalizes nothing. The same argument applies to all estimators. So it doesn't pick this maximum likelihood estimator as anything special. And this bottom line here, that why being closest to ideal target is better than being even closer to some other target, which is not necessarily ideal. So this leaves the question completely open. Oops. Okay. Now here I have again that NML, normalized maximum likelihood code. And now this is a theorem really, that any reduction of the numerator reduces the ratio, and that's what counts. The ratio is a code. That's what we want, not the numerator. And nevertheless, it has this property that if you don't use maximum likelihood estimator, you can't have the best largest ratio, which gives the shortest code length. And this property can also be rephrased, and the rephrasing turns out to be a sharp, complete form of MDL principle, because it says that no strings code word can be shortened by any estimated parameter. So you have to use maximum likelihood estimator without losing this property. Okay. Now here is then the general case where you also estimate the number of parameters, and you see that everything is perfectly analogous to the previous case. This time this hat k is by no means the maximum likelihood estimator. But everything is literally the same and intact. So now you see that this estimation capacity gives you something, gives you really a strong point-wise optimality. And to repeat, you use the same procedure for both cases, to estimate the real valued parameters and to estimate both. You don't need a new bundle of ad hoc criteria for estimating the number of components. Okay, let us then move to another way to justify optimalities. So instead of covariance, compare estimators by Kullback-Leibler distance, or this cross entropy, between data generating models in the class and the codes that are defined by estimators, by this normalization process. Now let me take a little reminder of something that has been done and have been known in or has been known in data compression for a long time. We start with the Minmax problem. We want a universal code for this model class where k, the number of parameters, is fixed. So we look for the universal code Q that minimizes the worst case Kullback-Leibler distance. Well, it's a difficult problem, and there is no neat solution to that. So clever people changed the problem by taking a prior and taking the mean of this Kullback-Leibler distance. Now there is an elegant solution for any prior. The best Q is simply the Bayesian mixture, that Q sub W. And then you ask for the prior that maximizes that max-min, and you get channel capacity, which is called in this context regret. Well, I'm just saying that this is not relevant for estimation. Beautiful result for data compression, but it has nothing whatsoever to do with estimation. Well, what would be the min-max problems that are relevant for estimation? Well, these two min-max problems, obviously. So we don't look for the minimum over all Q's of all distributions, but we look at the worst case minimum among the estimators. Those are the things that we are interested in. So those are meaningful and well-defined min-max problems. And this time we do have a solution to them. We don't need to take the mean with respect to some irrelevant prior. The first theorem simply says that the min-max problem is solved by our maximum likelihood estimator. And the distance is the estimation capacity. Very neat and nice. Now the estimation, this Kullback-Leibler distance is not constant. It does depend on the data generating model. However, it doesn't vary too much. But it does. It's not constant. And then the other theorem, for the case where you also estimate the number of parameters, we have a similar result. It is solved by the real valued parameters have a maximum likelihood estimator, but the other one is not. But it's the one that gives the estimation capacity. And the min-max value is again the sum of those two estimation capacities. Now, a long time ago, I proved this. This is the only result that did not need to be changed, or it's only written in a slightly different way. But we get automatically optimal convergence rate. No estimator can beat that bound. Okay. Now there is one of these criteria, there's multitude of criteria for estimating the number of parameters, is this Bayesian mixture, which has some priors. And now the simple fact is that that is not optimal, no matter which prior you take. So that settles that. Okay, let me then, I have a few more minutes. I want to say something about this. In traditional estimation, people also talk about interval estimation and robustness. And those are dealt with, again, as usual, purely by intuition. They are meaningful notions for the, but there is actually no, well, I was about to say that they don't, it's rarely explained why do we need them. Well, the reason is that the parametric model classes are too rich. They do not quite correspond to our intuition. Remember that we are after statistical properties in the data, in our measured, observed data. And then we express those properties by terms, in terms of these distributions. And you see that the family of models is far too rich. Like in Bernoulli case, you can't have more than 2 to the n properties. And yet, Bernoulli class is much, much, much bigger. So there is something in that class that we are using, even though I know that I don't want them. Well, so here's the intuition. The intent is to somehow cut off the effect of too much randomness. The estimated maximum likelihood value, parameter values, we know that they are shaky. Well, why are they shaky? Exactly because of that the class is too big. And instead, we would like to consider intervals of them. And that leads into this. Oops. Before I get to the interval estimation, let's see now. Yeah. We have to, of course, agree when do we call two estimated parameter values equivalent. Well, we call them equivalent if they assign the same density and when they fall in the same interval. So that flat top density G sub B. And then I found quite recently this interesting property, theorem really, that there is an interval of I denote the length by B hat, such that the rectangle that, oops, now I blew it. Okay, that this area is maximum. That's a funny property of at least Gaussian distributions. It doesn't have to be Gaussian, but it surely holds. That statement is true for Gaussians. So there is a special interval with maximum area. And this allows us to define estimation capacity for intervals. Okay. We again have, just for the sake of interest, Bernoulli family. These are, of course, fully general. So we have those rectangles, those flat top that define equivalences for estimators. And you see that I have been able to calculate. I can't use this. Okay, I'll have to show it otherwise. This Q, I could calculate the maximum area, and it gives an interval length, the optimal interval length, square root of 1 over n. And now we can calculate the capacity the usual way. We add all those probabilities together, and it is now maximized because each block was maximum. That's why I needed the very first result. And we define optimal code for the intervals. So again, it's perfectly analogous to the point estimation. Okay, now I'm getting close to the final foils, but I'd like to show something. We don't need to take those flat top rectangles as our models. They were simply to define equivalence in the estimators. And we can take the model defined by the centers of the intervals. And now we know we can calculate how many of those intervals there are. and I call those center points optimally distinguishable. This term originally started with Vijay Balasubramanian, but I have just added the word optimally and this interval estimation itself. His number was the C hat, which is an uncountable. Okay, yeah, one more thing. The size of that probability P sub D, that can be taken as a measure of confidence. What confidence I have that this interval includes the true data generating parameter. You see, this confidence business, of course, is done by the traditional statisticians, and they have truth, and they can meaningfully ask, what is the probability that this interval includes the truth? So I'm just imitating, playing a game here, respecting these great statisticians. Okay, so now we know. And this is an interesting, to me anyways, an interesting theorem, because it shows the analogy between Shannon's channel capacity and estimation. I don't need to spell you know Shannon's theorem that when you have a noisy channel, I can transmit long sequences in such a way that the error goes to 0. Well, here is a similar thing. See, my estimation capacity plays exactly the analogous role to channel capacity. The messages, they are now these center points that can be consistently, or these models that can be consistently estimated. And we have exactly analogous theorems. Okay, this brings me to the conclusion. So what have we done? The role of the universal models was changed simply to yardsticks to measure quality of estimators. The models themselves are of no particular interest to me. I would not use those models the way I would use models. And the preferred yardstick was defined by estimator capacity. And we got a formal justification for once for the maximum likelihood estimator, and I had to call the other estimator simply a generalization. It's not the maximum likelihood, the one where you estimate also the number of parameters. It should, of course, be given some name, but I couldn't find any. And the formal justification amounts to a new complete MDL principle. Complete means that the code words are shortest. There is nothing wasted. The craft inequality holds with equality and all that. I gave also 2 Minmax theorems in terms of the Kullback-Leibler distance, which obviously replaced Cramer-Rao inequality. And finally, I know that the statisticians are not going to like this. They say that it requires too much information theory. Well, my point is that learn your own field or study information theory. Thank you very much for that.
Okay, thank you, Jorma, for the sweeping and perhaps provocative talk, especially the last bullet item. We have time for a few questions. Especially welcome are the statisticians responding. Any questions? Actually, I have a question. So I was thinking as you were talking about optimal estimation, about the connection between this and the compressed sensing ideas that were presented in the first plenary talk. So is there any connection or application of MDL to the compressed sensing on a reduced subspace?
I cannot. I have to confess that I wasn't here.
Okay, all right. Maybe a topic for future research. No more questions?
Boy, this is such a huge audience.
Hi. It's actually two questions. The first one, I mean, at some point in your talk you said that our model shouldn't favor any data. And my impression is if you're using a parametric model, you're already favoring some data. And if you go and use a non-parametric model that can explain any data, it will probably overfit to your data. So I don't know if you can say something more about that. And the second question is about your estimator capacity concept. For me, maximizing the normalizing quantity of the mutual of the likelihood, it looks like the maximization of the evidence using Bayesian statistics. And I don't know if you can relate one to the other, or if there is any connection over that. Thank you.
Okay. Yeah. First, in general, the non-parametric, the question was about parametric models and non-parametric models. The non-parametric models are nonsense. The reason is that you can't write them even down. How can you fit them to data? You got to have something concrete. And secondly, these parametric models, they include, for instance, histograms. So I don't think anything or very little is lost.
Okay.
And that's it.
All right, that's it. Thank you, everyone, for your kind attention. Sessions will start shortly.